A very good morning to Dr. Hanif and fellow viewers of this video. Today we'll be discussing on the relevant concepts with regards to displacement current. And this video is presented by Gabriel Ganeshin, Ting Shi, Samuel Lo Yihang, Li Jiaqian, and Aisha Binti Mustafa, all of whom are members of Group 2. Now to start off this presentation, we ask ourselves, what is displacement current? In the field of electromagnetism, displacement current is the quantity that appears in Maxwell's equations and is known as the rate of change of electric displacement field. This means that we observe the rate of change of the displacement effects of an electric field on the charges within a dielectric material, such as polarization charges or bound charges. It can also be defined as a phenomenon analogous to an ordinary electric current, posited to explain magnetic fields that are produced by changing electric fields. Ordinary electric currents, called conduction currents, whether steady or varying, produce an accompanying magnetic field in the vicinity of the current. We might think to ourselves, how was displacement current discovered? Well, now we see the history of such an amazing discovery. The British physicist James Clerk Maxwell in the 19th century predicted that a magnetic field also must be associated with a changing electric field even in the absence of a conduction current, a theory that was subsequently verified experimentally. As magnetic fields had long been associated with currents, the predicted magnetic field also was thought of as stemming from another kind of current. Maxwell then gave it the name displacement current, which was proportional to the rate of change of the electric field that kept cropping up naturally in his theoretical formulations. As electric charges do not flow through the insulation from one plate of a capacitor to the other, there is no conduction current. Instead, a displacement current is said to be present to account for the continuity of the magnetic effects. In fact, the calculated size of the displacement current between the plates of a capacitor being charged and discharged in an alternating current circuit is equal to the size of the conduction current in the wires leading to and from the capacitor. Did you know that displacement currents actually play a central role in the propagation of electromagnetic radiation, such as light waves and radio waves? But that's only through an empty space. A traveling, varying magnetic field is everywhere associated with a periodically changing electric field that may be conceived in terms of a displacement current. In fact, Maxwell's insight on displacement current therefore made it possible to understand electromagnetic waves as being propagated through space completely detached from the electric currents in conductors. Moving on, we dive into the characteristics of displacement current. First of all, it is a vector quantity and is measured in amperes just like regular current, or what we call conventional current. Displacement current is not produced by the flow of electrons, but by the change in the electric field. Unlike regular conventional current, it does not follow Ohm's law and is not an actual current. And for that's why displacement current is always zero, especially for a closed path. Now I'd like to pass it on to Ting Shi, who will discuss on Maxwell's equations. Thank you.
Thank you for Gabriel Gan for explaining about the displacement current concept. Now, I want to give some description about the Maxwell equation related to the concept of the displacement current of electromagnetics. So, let me see the equation. So, at the left side, we can see the Maxwell equation is equal to divergence of H is equal to J, where the H is equal to magnetic field intensity and the J is the current density. And after we apply the divergence at the both sides, we can give the conclusion that the divergence of J is equal to 0. But at the continuity current equation, we can get the divergence of J is equal to negative d PV over dt, and where PV is the electromagnetic of volume. and we know this value is not equal to 0. So mean the first equation has some missing element, or the equation is not complete. So we see, so we add the G at the J, means we add the missing element. After we prove, we can get the divergence of G is equal to dPV over dt. So after that, we put the value of divergence of G into the general equation, and we substitute the PV to equal to the divergence of the D. So after that, we remove the divergence of the both side, and we get the final Maxwell equation. The final Maxwell equation say divergence of H is equal to J plus dt over dt. The J is mean the conduction of current in density, and the dt over dt is the displacement current density. In the other word is the change in magnetic flux that product the magnetic field. So means when have the change means it need the time to do. So when we don't have the time, so we not have the change, so mean the value of dt over dt will equal to 0. So let's see the example. The case 1 is for time varying field for the perfect dielectric. So means when we pass through the perfect dielectrics, if we are not resistor, so means the conductivity will equal to 0. So otherwise the J will equal to 0. So the J element will be cancelled out. So at the second, it is the normal dielectric, so it have the value of the conductivity, and the value of J will not equal to 0. So it will constant at the final equation. And next we see of the not time varying field. As I say at the before, the not time varying field means we don't have the time, so we don't have the changing of the magnetic flux and magnetic field. So this element, because it's affected by the time, so means if we don't have the time, so it will become 0. So if the equation is divergence of H equal to J. This diagram is more easy to see the effect of the perfect dielectric, the lossless dielectric. When we use the perfect, we call the lossless dielectric, it will only have a capacitor, and after we use the normal dielectric, it will have a resistor. That that is the value of J. So this is all for my present. After that, I will pass to my member, my group member, to present about the real world example of displacement current.
Now, I would like to talk about the real world example of displacement current, which is the current in capacitors. The diagram above shows a parallel plate capacitor in an electric circuit with no medium between the plates, which means there is free space between the plates. When the circuit is turned on, equal and opposite charges will accumulate on the parallel plates. As you can see from the diagram, positive charges accumulate on the left plate, whereas the negative charges accumulate on the right plate. During the charging process of the capacitor, electric field, or E field, between the plate will increase. However, no charges is transported through the free space between the plates. Now, we can notice that there is a magnetic field formed between the plates of the capacitor. This can be explained by the presence of displacement current. The displacement current flows through the free space, and this current produces the magnetic field in the region between the plates, according to Ampere's law. The magnetic field between the plate is the same as the outside of the plate, so we can deduce that the displacement current is the same as the conduction current in the wires. In short, the E field causes the displacement current, which causes the H field, which is the magnetic field.
Thank you.